Hello there, and welcome to Sleepy Science Vault. Somewhere out there, in the vast, quiet dark between the stars, something extraordinary exists. Something that cannot be seen, cannot be touched, and yet shapes the entire universe around it. Right now, as you drift into stillness, there are millions of black holes scattered across our galaxy alone. Millions. And almost none of them can be seen. They sit in silence, hidden in the dark, patient, still. A black hole only reveals itself when it begins to feed, when gas and dust and light spiral slowly inward, and the space around it begins to glow. But most of them are simply quiet, invisible, waiting, and in their silence, they are doing something profound. Every black hole bends the fabric of space and time around itself, not just a little, not gently, but completely. Space itself curves and warps and stretches in ways that feel almost impossible to imagine. Time slows down near a black hole. The closer you get, the slower time moves. Imagine that. Time becoming softer, becoming slower, drifting, the way you are drifting now, into something quieter. Scientists have discovered that black holes come in different kinds. 4 of them. Each one different in size and in scale. There are the small ones, stellar black holes, born from dying stars, compact and dense, and extraordinarily powerful. Then there are the giants, supermassive black holes, sitting at the centers of galaxies, billions of times more massive than our own sun. And somewhere between those two, scientists believe there may be others. Middleweight black holes, sometimes called intermediate mass black holes. They have never been found. Not quite. But the evidence is slowly building, quietly, the way most great discoveries happen. These intermediate black holes would bridge the gap between the small and the supermassive. A missing link, hiding somewhere in the dark. And the universe keeps surprising us. Recently, astronomers noticed something unusual. Something that didn't fit. Small, faint objects appearing in the deep reaches of space. They called them little red dots. And when scientists looked closer, they found something remarkable. These tiny red smudges of light contained black holes, far too massive for how young they were. Black holes that should not have had enough time to grow that large. And yet, there they were, quietly rewriting what we thought we knew. Even the black holes we do know about can hide from us. Around 35% of all supermassive black holes are shrouded in thick clouds of gas and dust, invisible to most of our instruments, concealed even from telescopes pointed directly at them, hidden in plain sight. But in 2019, something changed. For the first time in human history, we saw a team of astronomers working together across the entire planet, linked telescopes from different continents, and turned them all toward the same point in the sky. And there it was, a ring of glowing light, surrounding a deep, perfect darkness. The first image of a real black hole. It was called M87, a supermassive black hole, 6.5 billion times the mass of our sun. And humanity looked at it and was still. That image, that quiet ring of fire in the dark, reminded us how small we are, and how vast, and strange, and beautiful the universe truly is. So as you rest now, let that image sit gently in your mind. A ring of light around a perfect, peaceful darkness. Somewhere out there, millions of black holes drift through the galaxy. Silent, invisible, patient, and the universe holds them all quietly. In the dark, there is something deeply calming about beginnings, about understanding how things come to be. In the quiet of this moment, let yourself wonder about one of the most dramatic births the universe knows how to create. The birth of a black hole. Most people imagine a black hole forming in one particular way. A massive star, burning for millions of years, running out of fuel, and collapsing inward. And that does happen. It is real, and it is extraordinary. But there is another way. A way that is even more direct. Sometimes, a cloud of gas in the early universe does not bother forming a star at all. It simply collapses all at once, directly, straight into a black hole. No star, no explosion, no gradual burning out. Just collapse. Scientists call this direct collapse. And it may explain how some of the earliest and most massive black holes in the universe grew so large, so quickly, before most stars had even formed. Some black holes may have already existed, born not from death, but from pure, overwhelming gravity. Let that settle over you, like a slow, heavy stillness. Gravity, so strong that it skips every step in between. There is another way black holes are born. That is perhaps the most violent and the most beautiful event the universe produces. Imagine two neutron stars, the dense, collapsed remnants of stars that once burned, brighter than anything you can picture. Now imagine them, locked together in orbit, circling each other, closer and closer, over millions of years, spiraling inward, in a slow, inevitable dance, until finally, they collide. In an instant, the two neutron stars merge, and if the combined mass is great enough, the result is a brand new black hole, born in a flash of gravitational waves, and a burst of gold and platinum scattered across the cosmos, the universe, making something out of something else's ending. And it does not stop there. Black holes themselves can merge. Two black holes, drawn together by gravity, spiraling toward each other, across vast distances and unimaginable stretches of time. When they finally meet, they do not simply join quietly. The collision sends ripples through the fabric of space-time itself. Gravitational waves, invisible but real, traveling outward in all directions at the speed of light. We have detected these waves here on Earth with instruments so sensitive they can measure a disturbance smaller than a single proton. Think about that for a moment. As your breathing slows and your body grows heavier, and still, two black holes, billions of light years away, collide in the dark. And we feel it here. We feel the universe move. But when two black holes merge, something unexpected can happen. The newly formed black hole does not always stay still. Sometimes, the gravitational waves released in the merger are not perfectly symmetrical. They push out more strongly in one direction than another, and the new black hole gets kicked. Recoil, like a cosmic recoil, from the force of the merger itself. The black hole can be sent flying through its galaxy at hundreds of kilometers per second, sometimes even fast enough to escape the galaxy entirely. A black hole set loose in the open universe, drifting alone, wandering the dark between galaxies. There is something quietly poetic about that. And the universe has still more ways to make these things. Imagine a binary star system. Two stars orbiting each other, partners for millions of years. Now imagine one of those stars is already a black hole, a stellar black hole, sitting quietly beside its companion. The companion star grows. It swells into a giant and begins to spill its outer layers toward the black hole. Mass flows between them, and eventually, the companion reaches the end of its life. It explodes, A supernova. Brilliant and violent. Erupting right beside a black hole. The shock wave slams outward. The black hole survives. And in some cases, the explosion itself is shaped and triggered by the presence of the black hole nearby. The black hole participating in the death of its own companion. Quietly. Inevitably. Black holes can even detonate stars through close encounters alone. If a star passes near enough, the tidal forces of the black hole can stretch it, compress it, and in some cases, ignite a thermonuclear explosion within the star itself. Not by touching it, not by consuming it, but simply by being near it. Gravity, as a kind of invisible hand, reaching out across space. And while all of this destruction sounds immense, black holes also create, or rather, they regulate. In every large galaxy, the supermassive black hole at its center plays a quiet but essential role in how stars are born. When a black hole feeds, it releases enormous energy, jets of radiation, and powerful winds pour outward into the surrounding galaxy. These outflows push gas away. And without gas, stars cannot form. So in a strange and beautiful way, black holes slow down the creation of new stars. They act as a kind of governor, a regulator, keeping galaxies from burning through all of their star-forming material too quickly. Without this balance, galaxies would look completely different. The universe would look completely different. Even the intense radiation streaming away from a feeding black hole pushes gas outward in vast, slow streams. These outflows can stretch for thousands of light years, moving gas that might one day become stars, far away from where it began, sculpting the galaxy slowly over millions of years. And yet, for all their power, for all their enormity, there is evidence now that supermassive black holes may be smaller than we once believed. Our methods of measuring them are still being refined. Some estimates that seemed certain are now being reconsidered. Quietly, carefully, the universe gently correcting us, as it always does, reminding us that our understanding is always only partial, always growing, always reaching towards something just beyond what we can currently see. So as you lie here, and the quiet deepens around you, consider this. Every black hole in existence was born from something. A collapse, a collision, a merger, a death. Each one with its own origin, its own story, stretching back billions of years. And right now, somewhere in the universe, new black holes are being born. In silence, in darkness, in the slow, inevitable way that gravity always wins. Let that thought carry you gently downward into stillness. You are resting, and the universe is quietly building itself in the dark. Imagine you are traveling through the deep, quiet dark of space. No sound, no rush, just the slow, steady feeling of moving towards something vast, something that has been waiting for a very long time. Ahead of you, impossibly far away, and yet growing slowly closer, is a black hole. You are approaching, and as you do, let yourself notice the way everything around you begins to change. The first thing scientists speak of when describing the edge of a black hole is the event horizon. It is not a wall, not a surface, not something you could reach out and touch. It is a boundary, an invisible line, drawn across the fabric of space-time, beyond which nothing can return. Not matter, not energy, not even light. Once something crosses the event horizon, it is no longer part of our universe. Not in any way we can reach. Not in any way we can know. The event horizon is the point of no return. And yet, from a distance, it looks like nothing at all. Just darkness. Just the quiet absence of light. But as you move closer, something begins to happen to the light around you. Light from distant stars, traveling toward the black hole, loses energy on the way. It stretches. The wavelengths grow longer and longer, shifting slowly toward red, and then toward infrared, and then into frequencies the human eye cannot see at all. This is called gravitational redshift. The light does not disappear all at once. It simply fades, grows dimmer, grows redder, like a sunset that never quite ends, like the last warmth of a fire, slowly going out. Let that image settle over you now. A slow red fading at the edge of the most powerful thing in the known universe. And then there is time. Near a black hole, time does not behave the way it does here. The closer you get to the event horizon, the slower time moves. For you, relative to someone watching from far away. If someone far from the black hole were watching you approach, they would see you slow down. Your movements growing quieter, your image growing redder, until eventually you appear to freeze. suspended at the edge of the event horizon. Forever. From their perspective, you never cross. You simply hover there, still. But from your perspective, something stranger still would happen. Looking outward, away from the black hole, you would see the rest of the universe speeding up, stars aging, galaxies evolving, light shifting and changing across billions of years, compressed into the time it takes you to fall. You would watch the future of the universe play out before you, slowly at first, and then faster still, like watching time itself. Breathe in one final, accelerating breath. Imagine that. The entire future of everything, visible from the edge of a single black hole, and the universe simply continuing as it always has. Indifferent, magnificent, vast. Now, as you drift closer still, the environment around you becomes something almost impossible to survive. The region near a feeding black hole is flooded with radiation, X-rays, gamma rays, temperatures reaching into the billions of degrees. In the surrounding accretion disk, the material spiraling inward, compressed and heated, until it glows brighter than entire galaxies. Some of the most luminous objects in the universe are simply black holes, eating the glow of consumption, the light of an ending, burning across billions of light years, so that we, in our small, quiet corner of the cosmos, can look up and see it. But here, in this imagining, in this slow, calm journey, we continue, and the black hole is not still. Most black holes rotate. They spin, carrying the space-time around them, like water spiraling down a very slow and very enormous drain. This rotation creates something remarkable. A region just outside the event horizon, called the ergosphere. Inside the ergosphere, space itself is dragged along by the spin of the black hole. Nothing inside the ergosphere can remain still. Even light, even emptiness itself, is pulled around in the direction of rotation. You cannot hold your position there. The universe simply will not allow it. And yet, the ergosphere is still outside the event horizon. It is still, technically, escapable. If you had enough energy in exactly the right trajectory, you could enter the ergosphere and return. Changed, but returned. Now, here is something that may surprise you. For all their fearsome reputation, a supermassive black hole at the moment of crossing its event horizon, may be surprisingly calm. For a stellar black hole, small and dense, the tidal forces at the event horizon are crushing. The difference in gravity between your head and your feet would be catastrophic. But for a supermassive black hole, billions of times more massive, the event horizon is so far from the center that the tidal forces there are actually gentle. You could cross the event horizon of a supermassive black hole without feeling anything unusual at all. No dramatic moment, no violent sensation, just a quiet, invisible line crossed in the dark. And you would not even know until much later that you had passed it, that you were already inside. Let that thought drift through your mind like a slow, quiet tide. The most significant boundary in the universe, crossed without a whisper, and yet your body itself would tell a different story. In other ways, as light bends around the black hole, your own vision would distort. You would see light from stars behind you, bent around and appearing in front of you. You might even see the back of your own body, light from yourself, traveling away, bending around the black hole's gravity, and returning to your eyes. Gravitational lensing, so extreme, so complete, that the universe becomes a mirror. A curved, infinite, breathtaking mirror, wrapping around you in every direction. And then there are the photons, light itself, trapped at a precise distance from the black hole, called the photon sphere, or the photon shell. Particles of light can orbit, not falling in, not escaping outward, just circling endlessly. A shell of trapped light, glowing faintly, wrapped around the darkness. Light that has been traveling, perhaps for millions of years, caught in an orbit. It may never leave. There is something deeply still about that image. Light in a perfect, endless circle, going nowhere, and yet never stopping. And finally, as we rest here together at the edge of this imagining, it is worth knowing that modern physics has begun to see the event horizon itself in a new way. The classical event horizon, that sharp, absolute boundary, may be a simplification. Some physicists now speak of quasi-local horizons, boundaries that are more dynamic, more subtle, that depend on the observer, on the motion of things nearby, on the full, complex behavior of space and time, in ways we are only beginning to understand. The universe, once again, refusing to be fully contained by our current ideas, quietly insisting that there is always more, always something deeper, always something just beyond the edge of what we know. So as your breathing slows now, and the warmth of rest settles through you, carry this with you. Somewhere out there, light is orbiting in perfect circles around a darkness that bends time itself. The universe is spinning slowly at its edges, and you, here, still, are drifting gently into your own quiet dark, a boundary crossed without a sound. Rest now. The black hole is patient, and so is the night you have crossed. There was no sound, no sudden shift, no moment of alarm, just the quiet continuation of falling. And yet everything has changed. You are inside now, beyond the event horizon, beyond the boundary that separates the known universe from this place, this strange, dark interior. And the first thing to understand, the first truth of this place, is one that takes a moment to fully absorb. Nothing escapes from here. Not a single particle. Not a single photon of light. Not a whisper. Not a signal. Not the faintest trace of anything that crosses this threshold. The event horizon is not a door that swings both ways. It is a one-way membrane, and you have passed through it. But here, in the deep, slow quiet of this imagining, that is not a frightening thing. It is simply true, a fact of this place. Like the way night is simply dark. Like the way deep water is simply still. You are here. And here has its own rules. The most extraordinary of those rules is what happens to space and time once you cross the event horizon. Outside, in the familiar universe, time moves forward, always forward. You cannot stop it. You cannot reverse it. But space, you can navigate. You can move left or right, forward or backward, up or down. Space gives you options. Time does not. Inside a black hole, this arrangement reverses. Time and space swap their roles. The direction toward the singularity, the center of the black hole, becomes a direction in time rather than a direction in space. It is not somewhere you are moving toward. It is something you are moving into. The way you move into tomorrow. The way you move into the next breath. Inevitable. Unchangeable. The singularity is not a place in the way we usually mean. It is a moment, a future moment, that you cannot avoid, any more than you can avoid The next second, ticking quietly by. Let that wash over you slowly. Time becoming space. Space becoming time. The universe rearranging its most fundamental rules at the threshold of the unknown. And because of this, you cannot stay still. Outside a black hole, you can hover. You can hold your position in space with enough thrust, enough energy. But inside, there is no hovering. To remain stationary inside a black hole would be like trying to stop time. It cannot be done. You must move. Not because something is pushing you, but because stillness, in the direction of the singularity, is no longer physically possible. The geometry of space-time itself carries you forward, gently, inexorably, the way a river carries a leaf. Not with force, not with urgency, just with the quiet certainty of the current. And no engine, no matter how powerful, could reverse this. Imagine the most advanced spacecraft ever conceived. Engines burning at full capacity. Every possible force directed outward, away from the center. It would not matter, because moving outward inside a black hole is like trying to move into the past. The physics of this place simply do not allow it. There is no outward anymore. There is only forward, only deeper, only the slow, quiet continuation of the fall. Now, perhaps you have heard that black holes might be doorways, tunnels through space-time, passages to other places, or other times, or other universes entirely. Wormholes. It is a beautiful idea, and the mathematics, in certain forms, can seem to suggest it. But the reality, as best as we understand it, is different. A black hole is not a wormhole. Not in any way that could be used. Not in any way that allows passage, or escape, or arrival somewhere else. The singularity at the center is not an exit. It is simply an ending, a point where our equations stop making sense, where the known laws of physics reach their limit and go quiet, like a sentence that simply trails off into silence. And beyond that silence, we do not yet know. We have not yet found the language to describe what is there. Perhaps someday. But for now, the interior of a black hole keeps its deepest secrets perfectly. And speaking of secrets, nothing you experience in here can be communicated outward. Not a single piece of information, not a measurement, not an observation, not a signal of any kind to the universe outside. You have simply vanished. An observer far away, watching you fall, would see your image freeze and redden and slowly fade. They would never see you cross. They would never know what you found inside. The event horizon is the perfect wall of silence. Everything that enters alone, without echo, without reply. And yet, the black hole itself does know you are here, in the only way it can. Every particle that falls inside, every atom of matter, every photon of light, adds to the mass of the black hole. Your presence, however small, becomes part of it. You do not disappear. You are incorporated, folded into the black hole's gravity, its mass, its slow rotation, its gentle, enormous pull. The black hole grows by the smallest imaginable amount and carries that growth forward in time, forever. Now here is something that few people think about when they imagine a black hole. The interior is not small. It may not be small at all. The volume inside a black hole, the amount of space contained within the event horizon, may actually grow over time. Not the black hole as seen from outside. That grows only when it gains mass. But the interior geometry, the inner volume of space-time, may expand, even as the outer horizon remains the same. Like a room that is somehow larger on the inside than its outer walls suggest. Like a space that keeps quietly unfolding, deeper and deeper as time passes. The interior of a black hole may be vast, far larger than it appears, containing more room than the observable universe. In some theoretical models, a darkness with no visible walls, an interior that goes on and on and on. Let that image settle into you now, like the feeling of lying in an open field at night, beneath a sky that has no edges, no ceiling, no boundary, just depth in every direction. And within this vast interior, there may be something unexpected. Magnetic fields, not just outside the black hole, in the swirling accretion disk, but inside, threaded through the interior, like invisible lines of force, woven into the geometry of the collapsed space-time itself. Magnetic fields, surviving inside, shaping the environment. Even here, even in a place where light cannot escape, where time points only one direction, where space has rearranged itself into something almost unrecognizable, the universe still finds a way to leave its subtle patterns, its quiet signatures, its thread of order, inside the dark, and the dark itself is extraordinarily dense. The matter compressed inside a black hole reaches densities almost beyond imagining. A stellar black hole may contain matter compressed to 10 to the power of 20 kilograms per cubic meter. Numbers so large, they lose their meaning and become something closer to poetry. And for smaller black holes, the densities climb even higher. 10 to the power of 32 kilograms per cubic meter. A handful of space containing more mass than most people will ever have a frame to comprehend. Compressed, still, dense beyond the reach of ordinary language. And yet, even here, in this place of extremes, there is a strange kind of peace. The fall continues. Smooth, quiet, inevitable. No turbulence, no jarring. Just the slow, dark unfolding of the interior. Space widening around you as time carries you forward, as the singularity waits somewhere ahead, like a horizon that keeps its distance for now. So rest here for a moment, inside the largest inside there is, where time and space have traded places, where engines mean nothing, where light cannot leave, and secrets cannot escape, where the universe has folded itself into something so private, so complete, so utterly its own, that nothing outside will ever know what happens here. You are inside. The black hole holds you, the way deep sleep holds you, quietly, completely, without asking anything in return, just carrying you deeper and deeper into the dark. The fall continues. Deeper now. The vast, quiet interior, stretching around you in every direction. And yet, something is beginning to change. Slowly. So slowly at first that you might not notice. But the center, the true heart of this place, is closer now. And the closer it gets, the more the universe begins to show you its most extreme face. There is a word that physicists use for what begins to happen as you fall deeper toward the singularity. It is an unusual word, almost playful, for something so profound. Spaghettification. As gravity grows stronger, the difference in its pull between one end of your body and the other becomes measurable, and then significant, and then overwhelming. The gravity pulling at your feet, if you fall feet first, is stronger than the gravity pulling at your head. And this difference, this gradient, stretches you slowly at first, like taffy pulled between two hands, like a sound stretched into something lower and longer and quieter. You are being drawn out, elongated, thinned, into a long, narrow stream of particles and energy, spiraling inward in a small black hole. This would happen well before the event horizon. But here, in the vast interior, it begins only now, deeper in, closer to the center, where the gradient of gravity finally becomes too great to ignore. There is something almost meditative in imagining it, not with fear, but with wonder. The body becoming a thread, a single continuous line of matter, unraveling into the dark, becoming simpler, less complex, drawn towards something so fundamental that complexity itself cannot survive it. And the matter, that thread of particles, continues to fall, compressed now, beyond anything in ordinary experience, beyond the density of an atomic nucleus, beyond any state of matter we have a name for. It falls toward what physicists call the Planck density, a density so extreme that the very fabric of space-time may no longer behave as a smooth, continuous thing. At the Planck scale, space itself may become granular, foamy, broken into tiny discrete pieces, smaller than anything we can currently measure. The smooth geometry of the universe becoming something more like a texture, a grain, like the surface of still water, examined so closely that you begin to see the individual molecules. The smoothness was always an illusion, and beneath the illusion, something stranger, something we do not yet have the full mathematics to describe. All matter, everything that has ever fallen into this black hole, everything that was once a star, a cloud of gas, a wandering comet, a photon of ancient light, is being pulled in the same direction, toward the center, toward the singularity. That one inevitable point. And the singularity itself is perhaps the strangest thing in all of physics. It has no size, no volume, no width, no depth, no length. It occupies no space in any dimension. It is a point in the purest mathematical sense, a location without extension. All the mass of the black hole compressed into something that takes up and no room at all. Infinite density, zero dimensions. And at this point, the laws of physics, as we know them, simply stop. They do not bend. They do not strain. They end. Our equations, which have described the universe with breathtaking precision for over a century, reach the singularity and return. Only the word infinity and infinity in physics is not an answer. It is a signal, a gentle, insistent signal that the theory has reached the edge of its own understanding, that something is missing, that the map does not cover this territory. And so we stand at the edge of our knowledge, looking inward toward a center we cannot see, governed by rules we have not yet written. There is something deeply humbling about that, and something quietly beautiful, because we can only observe a black hole from the outside. Everything we know, everything we have measured, everything we have confirmed, comes from what leaks outward. Gravitational waves, the behavior of orbiting stars, the glow of infalling gas, the shadow of the event horizon, captured by telescopes, linked across a planet. But the interior has never been observed, cannot be observed by anyone remaining outside. The inside of a black hole is the most private place in the known universe, and to truly understand it, we need something we do not yet have: a theory of quantum gravity, a framework that could marry the two great pillars of modern physics that have so far refused to fully combine: general relativity, Einstein's theory of gravity, which describes the universe at its largest scales, and quantum mechanics, which describes the universe at its smallest. Both theories are extraordinarily precise in their own domains. Both have been tested and confirmed again and again. And yet, at the singularity, they speak different languages. They give different answers. And we do not yet know which one to trust, or whether both must be replaced by something deeper still, something we have not yet imagined. Two roads into the dark: string theory and loop quantum gravity, each reaching toward that unified understanding. String theory, imagining that the most fundamental things in nature are not particles, but tiny, vibrating strings of energy, each one oscillating at its own frequency, each frequency corresponding to a different particle, a different force, a different piece of the universe, a cosmos made of music, at its most fundamental level, vibrating in dimensions we cannot directly perceive. And loop quantum gravity, taking a different path, imagining that space itself is not continuous, but woven from discrete loops, tiny, interlocking quantum threads, that make up the fabric of space-time. The way stitches make up a fabric. Each approach, reaching toward the interior of the black hole, from a different direction, neither yet complete, both pointing at something real, something waiting to be understood. And the interior of a black hole demands even more than this. It demands physics beyond the standard model, beyond our current catalog of particles and forces. The standard model, that elegant and powerful framework, describing all the known particles, and 3 of the 4 fundamental forces, goes quiet here. It has nothing to say about the singularity, about the Planck density, about the moment when space-time becomes something other than what our instruments can measure. And so the interior of a black hole is not just a physical mystery. It is an invitation, a place where the universe is asking us to think more deeply, to go further, to build the tools of understanding that do not yet exist. And then, even before we reach the singularity, even here, in the deep interior, the quantum world begins to whisper at the very smallest scales. Space-time itself may not be smooth. Quantum fluctuations, tiny, probabilistic, shimmering uncertainties, ripple through the geometry of the interior. Space and time, at the Planck scale, do not sit still. They tremble. They flicker. Small bubbles of curvature, forming and dissolving in intervals so short they make a nanosecond feel like an eternity. The fabric of reality, at its most fundamental, is not a still surface. It is a living thing, restless, uncertain, governed not by certainty, but by probability, by the strange, beautiful, irreducible fuzziness of the quantum world. Even here, even inside the most extreme environment, the universe has to offer. The quantum nature of reality asserts itself quietly, persistently, like the sound of your own breathing in a perfectly silent room. Always there, even when you forget to notice. So as you rest now, and the darkness around you grows deeper and softer, and your thoughts begin to slow and drift, consider this. At the very heart of everything, at the place where all our maps run out, at the singularity, where dimensions vanish and physics falls silent, the universe is not empty. It is full of questions, full of trembling, flickering, quantum uncertainty, full of the unwritten laws of a physics we have not yet learned, full of the quiet hum of something just beyond understanding. And you, here, resting, drifting, are part of the same universe that contains all of this. The same atoms, the same quantum fields, the same fundamental uncertainty, woven into your own existence. At the smallest possible scale, you are made of the same stuff as the thing that falls toward the singularity. The same particles, the same forces, the same deep, unresolved, beautiful mystery. So let go now. Let the questions float. Let the singularity remain what it is. A point of pure, perfect, unknowing. And let yourself fall, in your own quiet way, into the soft, dimensionless, dark of sleep. Even here, in the deepest dark, in the most extreme place, the universe has to offer. Something extraordinary is happening. Something so subtle, so quiet, that it seems almost impossible. In a place like this, the vacuum itself is not empty. Stillness, at the quantum level, is not truly still. Even in the perfect void, in the absence of any particle, any photon, any measurable thing, the quantum world cannot quite be at rest. It flickers. Pairs of particles, born from nothing, for an instant, so brief, it barely qualifies as time at all. A particle and its antiparticle appearing together out of the trembling uncertainty of empty space, and then, almost immediately, coming back together and vanishing, annihilating each other as quietly as they appeared. These are called virtual particles. And in ordinary space, they borrow existence and return it so quickly that nothing is disturbed. The books of the universe balance perfectly. But here, at the edge of the event horizon, something different happens. Something that took one of the greatest minds of the 20th century to see. Sometimes, a virtual pair appears right at the boundary, one particle on each side of the event horizon, and before they can reunite, before they can annihilate, one of them falls inward, and the other escapes into the universe as a real particle, a particle that should not exist, and yet does, carrying energy outward, away from the black hole. This is Hawking radiation, named for Stephen Hawking, who first described it in 1974. A prediction so surprising that even Hawking himself found it difficult to believe. At first, a black hole, the most consuming thing in the universe, slowly radiating, losing energy, particle by particle, over unimaginable stretches of time. The black hole is glowing so faintly, so incredibly faintly, that no instrument we currently possess could detect it. For a stellar black hole, the temperature of Hawking radiation is a fraction of a billionth of a degree above absolute zero, colder than the cosmic microwave background, drowned out entirely by the ambient warmth of the universe itself. And yet, it is there, theoretically, quietly leaking into the void, like the faintest breath from something that was never supposed to exhale. Let that image rest with you for a moment. A black hole, breathing out, one particle at a time, over trillions and trillions and trillions of years. And because Hawking radiation carries energy away, the black hole slowly loses mass. It shrinks, almost imperceptibly, but shrinking. Given enough time, a black hole will evaporate entirely. The most powerful structure in the universe, undone by the quiet persistence of quantum uncertainty, by the fact that emptiness cannot hold perfectly still. There is something deeply peaceful about that. The grandest things ending in the gentlest possible way, not with a collision, not with a shock wave, but with a slow, patient, particle by particle, dissolving. And as our understanding of Hawking radiation deepens, physicists have found that the thermodynamic properties of black holes can be calculated with greater and greater precision. Temperature, entropy, energy. A black hole, it turns out, behaves in many ways like a thermodynamic object, like a body with heat, with a temperature that depends on its mass. The smaller the black hole, the hotter it runs. As it shrinks through Hawking radiation, it grows warmer, radiating faster, shrinking faster still, until in its final moments, a black hole may release an enormous burst of energy in a last, brief flash, before vanishing entirely. A lifetime of patient darkness, ending in a moment of light. And for charged black holes, those carrying an electric charge, quantum fluctuations add another layer of subtlety. The charge interacts with the quantum vacuum in ways that modify the radiation, the thermodynamics, the precise way energy leaks outward. Each black hole carrying its own subtle signature in the way it fades, like a fingerprint written in quantum light. Now, one of the most celebrated results in the theory of black holes is something called the area law, proposed by Stephen Hawking. It states that the surface area of a black hole's event horizon can never decrease. In any process, in any interaction, the horizon can grow or stay the same, but it cannot shrink. This mirrors a fundamental law of thermodynamics, the law that entropy, the disorder of a system, can never decrease. The area of the event horizon, i.e. the entropy of the black hole, a measure of how much is hidden inside, how much information has been swallowed and concealed. And recently, using gravitational wave data from merging black holes, physicists were able to verify Hawking's area law observationally for the first time. Before the merger, they measured the areas of the two horizons. After the merger, they measured the area of the new, combined horizon, and the final area was larger. As predicted, a 50-year-old theoretical result, confirmed by the collision of two black holes over 1 billion light-years away. The universe, quietly checking our homework and finding it correct. But even as one mystery resolves, another, deeper mystery remains. The information paradox. In quantum mechanics, information is never truly destroyed. The precise details of any physical system, its position, its momentum, its quantum state, are always preserved. Somewhere, they may be scrambled, they may be hidden, but they are never gone. This is one of the deepest principles of quantum theory. And yet, when matter falls into a black hole, and the black hole slowly evaporates through Hawking radiation, what happens to that information? The radiation that escapes appears to be completely random, thermal, featureless, carrying no trace of what fell in. A star, a planet, a book, a human being, all of it seemingly erased. This is the information paradox, and it troubled physicists for decades, including Hawking himself. Because if information is truly destroyed, then quantum mechanics, one of the most precisely verified theories in all of science, is violated. Something must give. And the leading answer, the idea that has gained the most traction, is remarkable. The information is not inside the black hole. It is on the surface, encoded on the event horizon itself. Every particle that falls in, every quantum of information, leaves a faint imprint on the two-dimensional surface of the horizon, like a shadow, like a hologram, the full three-dimensional story of everything inside, written on the boundary, in a language we are only beginning to learn to read. This idea connects to something called the holographic principle, the suggestion that the interior of any region of space can be fully described by information on its boundary, that the universe itself may be, in some profound sense, a hologram of three-dimensional reality, encoded on a two-dimensional surface, somewhere we cannot see. Let that drift through your mind, slowly, like a thought in the moments just before sleep. Everything real, written on a boundary, depth as a kind of projection. And then Stephen Hawking, in one of his final great contributions, proposed something further still. He called it soft hair, the idea that black holes are not as featureless as once believed, that they carry extremely subtle quantum imprints on their event horizons, soft photons, soft gravitons, particles of essentially zero energy, that record the passage of everything that falls through the black hole, remembering, in the quietest possible way, not loudly, not obviously, but there, a record, a soft, whispered memory of everything it has ever consumed. And the latest thinking goes further still. When physicists model the full process of a black hole forming and then evaporating completely through Hawking radiation, they find something hopeful. The process is unitary, a technical word with a profound meaning. It means that information is conserved, that what goes in comes out, transformed beyond recognition, scrambled into the most complex possible form, but present, carried in the subtle correlations between particles of Hawking radiation, emitted across billions and trillions of years. The black hole does not destroy what it swallows. It encrypts it, holds it, and slowly, patiently, releases it back into the universe in a form so deeply scrambled that recovering it would require knowing the exact quantum state of every particle ever emitted. Practically impossible, but theoretically preserved. And in quantum gravity, in the full theory we are still building, this unitarity holds even more completely the universe, keeping perfect books. Nothing truly lost, nothing truly gone, only transformed, only hidden in a deeper layer of the real. So as you rest here, as your breathing deepens, and your thoughts grow softer, in the boundary between waking and sleep becomes as thin as an event horizon. Carry this with you. Nothing that enters the dark is truly lost. It is held, encoded, written on the surface of the night itself, in soft, quiet patterns, too subtle to read, but perfectly preserved. You are safe in the dark. The universe remembers everything, and it holds all of it gently in the quantum folds of its infinite, patient keeping. Rest now. Let the information of this moment be written on the soft surface of your sleep. Nothing is lost. Nothing is ever truly lost. There is something waiting just ahead. Something we have been moving toward. Through all of this. Through the vast, quiet exterior. Through the crossing of the horizon. Through the deep interior. And the quantum flickering of the vacuum. Something at the center of everything we have explored. But before we arrive, before we reach that final point, something remarkable begins to happen. The story changes. We begin with entanglement, one of the strangest and most beautiful phenomena in all of quantum mechanics. Two particles, linked, no matter how far apart they are. The quantum state of one is connected to the quantum state of the other. Measure one, and you instantly know something about its partner. Across a room, across a galaxy, across any distance at all. Einstein called it spooky action at a distance, and he did not mean it as a compliment. And yet, it is real, confirmed by experiment. Again and again, the universe, allowing connections that seem to defy everything we intuit about separateness. But inside a black hole, something happens to entanglement. The extreme curvature of space-time, the quantum nature of the interior, disrupts these delicate connections. Entanglement, that most fragile of quantum threads, begins to break down. Particles that were once linked across the event horizon find their connection strained, severed. The quantum correlations that were so carefully, so precisely maintained in the outside universe cannot fully survive. In here, the black hole is not merely a physical extreme. It is a place where the very fabric of quantum connection comes undone, where entanglement, one of the deepest features of the quantum world, meets its limit. And it is not only entanglement that the interior challenges. Quantum gravity itself, the theory we are still building, the bridge between the large and the small, introduces something called decoherence. In quantum mechanics, a system can exist in a superposition, multiple states, multiple possibilities, all real, all overlapping, until a measurement or an interaction collapses them into one. This is the quantum world in its full, strange, unmeasured state. But decoherence is the process by which this quantum superposition fades when a quantum system interacts with its environment, with other particles, with other fields. The possibilities blur together. The quantum character washes out, and a definite classical reality emerges. Inside a black hole, quantum gravity causes this decoherence. At a profound level, the geometry of space-time itself, fluctuating at the Planck scale, interacting with everything, constantly, inevitably, causes the quantum nature of matter to wash into something more classical, more definite, as if the black hole, in all its density, in all its extremity, is forcing the quantum world to make up its mind, to choose, to become one thing. And yet, despite all of this, despite the broken entanglement and the gravitational decoherence, the interior of a black hole is not necessarily a place of contradiction. There is a principle in quantum mechanics called complementarity. It tells us that different observers can have different but equally valid descriptions of the same event. An observer falling into a black hole and an observer remaining safely outside will disagree profoundly about what happens at the event horizon. To the outside observer, infalling matter appears to freeze and slowly burn away in a wall of Hawking radiation. To the infalling observer, nothing dramatic happens at all. A smooth crossing, a quiet continuation. Both descriptions are true. Both are consistent with the laws of physics, as seen from each perspective. And crucially, no single observer can ever verify both. The universe, protecting its own consistency by ensuring that the two perspectives can never be directly compared. Complementarity, the idea that reality may be observer-dependent, not in a vague or philosophical sense, but in a precise, mathematical, physical sense. Different truths for different vantage points, each one complete, each one valid, each one a facet of something larger that no single perspective can fully contain. And then there is the holographic interior. We touched on this before. The idea that the surface of a black hole, its event horizon, encodes everything inside. But the implications go deeper still. Inside a black hole, space-time itself may not be fundamental. It may be emergent, arising from something more basic, from quantum information, from entanglement, from the patterns encoded on the boundary. Space-time, the smooth, curved geometry that we move through and call reality, may be a kind of projection, a hologram, built from the information on the surface of the horizon, the interior, generated not from geometry, but from quantum relationships, from the connections between pieces of information on the boundary. If entanglement creates space-time, then inside a black hole, where entanglement breaks down, space-time itself may begin to dissolve, to lose its coherence, to become something that our current language has no words for. Let that thought move through you, slowly, like a tide pulling back from a shore. Space as something built rather than something given. Reality assembled from relationship rather than substance. And if space-time can emerge, it can also unemerge. And at the center of a black hole, perhaps it does. But here, something in the story shifts. Something hopeful enters. Something that changes the ending we thought we knew. Because the singularity, that dimensionless point, that place where physics breaks down and infinity appears, may not be real. It may not actually exist. The singularity in the equations of general relativity appears when we apply those equations beyond their range of validity, when we push the mathematics into a regime where the theory itself no longer applies, and the result is not a physical prediction. It is a warning, a signal that something is missing, that the equations need help. And quantum mechanics may provide exactly that help. The uncertainty principle, one of the deepest laws of the quantum world, tells us something important. You cannot know with perfect precision both the position and momentum of any particle. The more precisely you pin down one, the more uncertain the other becomes. And this uncertainty is not a limitation of measurement. It is a feature of reality itself. Things do not have perfectly precise positions and momenta. At the same time, the universe, at its smallest scale, is irreducibly fuzzy. And this fuzziness, this irreducible quantum uncertainty, may be exactly what prevents the singularity from forming. As matter is compressed toward a single dimensionless point, the uncertainty principle pushes back. The more confined a particle becomes, the more uncertain its momentum, the more energetically it resists further confinement. And this resistance, this quantum pressure, may be enough to prevent the final collapse, to stabilize what general relativity says should become a singularity, to replace the infinite with something finite, something physical, something real. One proposal, emerging from string theory, is particularly beautiful. The fuzzball. In string theory, the fundamental objects are not points. They are strings. Tiny, vibrating filaments of energy. And when enough strings come together under extreme compression, they do not collapse to a point. They spread out. They weave together into a dense, tangled quantum structure that fills the entire volume of what we thought was a black hole interior. A fuzzball. No singularity. No infinitely dense point. No place where physics breaks down. Just an extraordinarily complex quantum object, filling space with vibrating strings and quantum information. The entire interior, full, not with classical matter, not with a geometric spacetime, but with something more fundamental, something from which spacetime itself might emerge. And string theory is not alone. In this hopeful revision, other approaches to quantum gravity also suggest that corrections to general relativity near the Planck scale can eliminate the singularity. Gravity, modified at the smallest scales by quantum effects, behaves differently than the classical equations predict. The collapse slows, stops, or transforms into something else entirely. A bounce, a transition, a new phase of existence, beyond what any current theory can fully describe. And in this light, black holes may turn out to obey the laws of physics. After all, not the laws as we first wrote them, but the deeper laws, the fuller laws, the ones we are still learning to read, the ones the universe has been patiently waiting for us to discover. And then there is Roy Kerr, the mathematician who, in 1963, found the exact solution to Einstein's equations for a rotating black hole, one of the most important solutions in the history of general relativity, a solution that bears his name still, the Kerr black hole. And in his later years, Kerr made a striking claim. The singularity, he said, does not physically exist. Not in any real, material sense. The mathematics permits it. But mathematics permits many things that nature does not actually do. Kerr argued that the singularity is an artifact, a feature of the equations, in a regime where the equations should not be trusted, that the real universe, governed by quantum mechanics and by the fuller physics we have yet to complete, will not produce a true singularity. The man who spent his life studying rotating black holes, looking at the center, and saying, quietly, carefully, with the authority of decades of understanding, it is not there. Not in the way we feared. Not in the way the classical equations suggest. The universe does not break down at its center. It transforms. It becomes something new. Something we have not yet learned to describe. But something that obeys rules. Something that makes sense. Somewhere beyond the edge of our current understanding. Let that be a comfort as you drift now into the quiet. The center holds, not with the cold perfection of infinity, but with the warm, uncertain, endlessly surprising logic of a universe that always has more to offer than we expected. The singularity may be a door rather than a wall, a threshold into a physics we have not yet written, and beyond it, not destruction, not infinite density, not the end of meaning, but something else, something waiting, quietly, to be understood, just as you are resting now at the threshold of sleep, not ending, transforming, becoming something quieter and deeper and more still. The singularity is not real, and neither is the boundary between waking and the soft dark of dreaming. Cross it gently. The universe holds everything together. On the other side, we have traveled far, through the outer dark, through the event horizon, through the deep interior, and the quantum flickering at the edge of the singularity. And now, something in the journey begins to feel different, not darker, not more frightening, but somehow more open, as if the universe, having shown us its most extreme face, is now quietly, gently, suggesting that even here, there is order. Even here, there are rules. Even here, physics does not abandon us. Not all singularities are the same. This is something that took time for physicists to fully appreciate. The singularity at the center of a perfectly spherical Non-rotating black hole is one kind, a space-like singularity, a moment in time, rather than a place in space. Unavoidable, in the way tomorrow is unavoidable. But rotating black holes, the Kerr black holes, the kind that most real black holes in the actual universe are believed to be, have a different kind of singularity. A ring singularity. Not a point, but a ring. A circle of infinite density, lying in a plane, at the center of the rotating geometry. And the behavior near this ring, the structure of the space-time around it, is different, more complex, more nuanced, with regions that might, in principle, be navigated around. The geometry of realistic black holes is richer and stranger, and in some ways, more forgiving than the simplest models suggest. The universe, as always, more intricate than our first approximations. And there is another kind of black hole that physicists have been exploring with growing excitement. Regular black holes. Not regular in the sense of ordinary. Regular in the technical sense of having no singularity at all. Black holes with event horizons, with all the external properties we associate with black holes, but with interiors that remain finite, curved, dense, extreme, but finite. No point of infinite density. No place where the equations break down. A black hole that is complete, well-behaved, all the way to its center. And remarkably, these regular black holes obey the laws of thermodynamics, the same laws that govern steam engines and ice cubes, and the slow cooling of a cup of tea on a quiet evening. Temperature, entropy, energy, all well-defined, all finite, all behaving exactly as the laws require. The most extreme objects in the universe, following the same rules as the most ordinary processes of everyday life. There is something deeply satisfying about that. Something that feels like the universe reassuring us that its laws are not fragile things, that they hold, even here, even in the most compressed, most curved, most extreme corner of physical reality. And these regular black holes can form without exotic matter. This is important. Some theoretical constructs, wormholes, certain speculative geometries, require matter with negative energy density. Exotic matter, something that may not exist in the universe we inhabit. But regular black holes, in many theoretical models, form from ordinary matter, from the same gas and dust and stellar debris that forms everything else. No exotic ingredients required. Just quantum gravity. Doing what quantum gravity does. At the smallest scales. Modifying the collapse. Smoothing the singularity. Replacing the infinite with the merely extraordinarily dense. And the thermodynamics of these objects holds universally, not just for particular solutions, not just for special cases, but across a wide range of regular black hole models. The laws of thermodynamics remain intact. The first law, the second law, energy is conserved. Entropy does not decrease. The universe, keeping its accounts, even inside objects that seem to defy accounting. And where do these regular black holes come from? They emerge from quantum gravity corrections, from the modifications that a full theory of quantum gravity would make to the classical equations of general relativity. Near the Planck scale, near the regime of extreme density, quantum effects change the geometry. They introduce a kind of pressure, a resistance, a quantum stiffness that prevents the final, total collapse. And the result is a black hole that looks identical from the outside to any other black hole. Same mass, same spin, same charge, same gravitational pull, but with an interior that remains physically meaningful. An interior where physics continues to speak, where the laws hold their shape, where the universe does not give up on making sense. And what is perhaps most remarkable is that we do not need a complete theory of quantum gravity to begin testing these ideas. We do not need to wait for the final unified theory, the one that reconciles general relativity and quantum mechanics fully and completely. We can already look for signatures, for observational hints that quantum corrections are present in real black holes, in the gravitational waves, from merging black holes, in the precise shape of black hole shadows, captured by telescopes, in the subtle details of Hawking radiation. If we ever develop instruments sensitive enough to detect it, the full theory may still be decades away. But the fingerprints of quantum gravity may already be visible to those who know where to look, and the laws themselves, even at the singularity, may not be absent. They may simply be transformed, written in a language we have not yet learned to read. The universe, not abandoning its own rules at the moment of greatest extremity, but expressing them in a form so compressed, so fundamental, so far from ordinary experience, that our current mathematics can only gesture toward them, like trying to describe music to someone who has never heard a sound. The music is real. The laws are real. We simply need a new vocabulary. And now, the journey opens into something wider still, something that moves from the firmly theoretical into the realm of the genuinely, breathtakingly speculative. Because the singularity, even if it exists, even in some modified, quantum-corrected form, may not be the end. It may be a beginning. There are physicists, serious physicists, working within rigorous mathematical frameworks, who suggest that what lies at or beyond the singularity is not termination, not a wall, not an ending, but a transition, a passage into something else, another region of space-time, another universe. The idea comes in several forms. In loop quantum cosmology, the Big Bang itself may have been a bounce, a previous universe, collapsing under its own gravity, reaching a state of extreme density, and then, rather than ending, bouncing outward into a new expansion, into our universe. And if that is what the Big Bang was, then perhaps the singularity inside a black hole is the same kind of thing. Not an ending, a bounce, a new beginning. On the other side, a new region of space-time, expanding outward from the moment of maximum compression. A daughter universe, born inside a black hole of its parent. Think about that. Very slowly, as you rest here, in the quiet. Every black hole, a seed. Every singularity, a moment of becoming. The universe, reproducing itself in the dark, at the hearts of its most extreme objects. Our universe, perhaps, born inside a black hole of some larger cosmos we can never observe. And within our own universe, black holes forming, and at their centers, new universes, budding outward, into dimensions we have no access to. An infinite, nested, quietly proliferating family of universes, each one born from compression, each one expanding into its own vast space, each one, perhaps, capable of forming its own stars, its own black holes, its own new universes, a cosmic recursion, a universe, dreaming itself endlessly into existence. And this is not merely poetry. There are mathematical frameworks that support it. Models in which the parameters of physics, the constants of nature, the strength of gravity, the mass of the electron, the speed of light, vary slightly from universe to universe, selected over cosmic generations for the ability to produce more black holes, more seeds, more offspring, a kind of natural selection for universes. The physicist Lee Smolin called this cosmological natural selection. The idea that we live in a universe whose physical constants have been tuned, not by design, but by the same blind, patient, iterative process that shapes living things here on Earth. Our universe, the descendant of countless others, its laws, the accumulated inheritance of cosmic generations. And whether or not this is true, whether or not black holes really do lead to other universes, there is something in the idea that feels right, something that resonates with the deepest patterns we see in nature. Nothing ends without beginning something else. No door closes without another opening somewhere. No compression, however extreme, is the final word. The universe, at every scale we have ever examined, finds a way to continue, to transform, to begin again, and perhaps, at its most extreme point, at the singularity, at the heart of the dark, it does the same. It continues, in a way we cannot see, in a direction we cannot point to, into something that has no name yet, in any language we speak, but real, ongoing, alive with the same laws, the same deep structure, the same quiet order that governs everything we have ever known. So let this be the thought that carries you now into sleep. You are resting inside a universe that does not end, that transforms, that continues, that finds, in its most compressed, most extreme, most unknowable moments, a way to become something new. The singularity is not a full stop. It is a breath, held for an instant, before the next. Long, slow exhale. And you, here, now, are also continuing, breathing, drifting, transforming the day into the quiet, open, boundless space of sleep. The universe goes on, and so do you, gently, without effort, into the dark. That is not an ending, but a beginning you will not remember making. Rest now. The next universe can wait. We are deep now, deeper than the event horizon, deeper than the outer darkness, deeper than the quantum flickering of the vacuum. And yet, the journey has more to offer. The geometry of the interior is not simple. It never was. And now, as we move further in, it reveals another layer, another boundary, another horizon, inside a rotating black hole, inside the Kerr geometry, the kind that most real black holes are believed to inhabit. There is not one horizon. There are two. The outer event horizon, the one we crossed so quietly, so unremarkably, some time ago. And then, deeper in, a second boundary, the inner event horizon, also called the Cauchy horizon, named for the mathematician Augustin Louis Cauchy, who studied the kinds of equations that govern how information travels through space-time. The Cauchy horizon is a different kind of boundary from the one we crossed before. The outer event horizon was a boundary of no return. Nothing could pass outward through it. But the Cauchy horizon is something stranger still. It is a boundary of predictability. In our ordinary universe, physics is deterministic. In a certain sense, if you know the state of a system perfectly, completely, you can predict its future. The equations of general relativity and of quantum mechanics allow this kind of prediction. They allow the future to be calculated from the present. But at the Cauchy horizon, this predictability breaks down beyond this boundary. The information about the outside universe, all of it, compressed into an instant, arrives simultaneously. Every signal, every photon that has ever fallen toward the black hole since the beginning of time reaches this surface at once. An infinite amount of information arriving in a single moment. And beyond this horizon, the equations of general relativity cannot uniquely determine what happens next. Multiple futures become possible. The mathematics offers more than one answer. And when mathematics offers more than one answer, physics is telling us something important, that we have reached the edge of what the theory can predict. The Cauchy horizon is where determinism quietly ends, and something else begins. In the classical equations, what lies beyond the Cauchy horizon is technically possible to pass through. Unlike the outer horizon, which is a one-way membrane, the Cauchy horizon may permit passage. A traveler falling inward might cross it and continue into a region of space-time beyond the singularity, into a place where the geometry opens up into something unexpected, something that the mathematics only partially and cautiously describes. And the universe itself, in its largest scales, also plays a role in the story of black holes, cosmic expansion, the slow, accelerating stretching of space itself that carries galaxies apart over billions of years, interacts with black hole properties in subtle ways. The cosmological constant, the energy of empty space itself, affects the geometry of black hole solutions. There are black hole spacetimes, called de Sitter black holes, that incorporate this cosmic expansion directly into their geometry. And in these solutions, the interplay between the compression of the black hole and the expansion of the cosmos creates structures richer and more complex than either alone, the very large and the very small, always connected, always in conversation. But the region beyond the Cauchy horizon is not a comfortable place to make predictions. As physicists like to say, beyond the Cauchy horizon, all bets are off. The classical theory offers no firm ground. The usual tools, the usual equations, the usual expectations become unreliable. It is not that chaos reigns. It is that our maps run out of detail. The territory continues, but the cartographers have reached the edge of what they can draw with current instruments. And so we turn again to quantum gravity, to the frameworks that reach beyond the classical limits. And one of them, loop quantum gravity, has something remarkable to say about what happens at the center in ordinary gravity. In Einstein's general relativity, gravity is always attractive. Mass attracts mass. Geometry curves inward. Collapse proceeds without resistance. But in loop quantum gravity, something changes at the Planck scale when matter is compressed to the fundamental granularity of space-time, to the discrete loops from which geometry itself is woven. A new force emerges, a repulsive force, not the repulsion of electric charges, not a new particle or field, but a quantum geometric repulsion, a resistance built into the fabric of space itself. At its most fundamental level, when space is compressed beyond a certain point, it pushes back. And this repulsion, this quantum geometric pressure, does something extraordinary. It stops the collapse. Not gradually, not partially, but completely. The singularity That infinitely dense point. That place where everything breaks down. Is not destroyed. It is bypassed. The matter that was falling inward. Inexorably. Inevitably. Hits this quantum repulsion. And bounces. Not violently. Not with a crash or a shockwave. But with the slow, inevitable, geometric certainty of a law of physics, doing exactly what it is supposed to do. The collapse reverses, and what was falling inward begins, very slowly, to expand outward. Into what? Into another region of space-time. A region beyond the singularity. That never actually formed. A region where the geometry opens up again. Where space-time breathes out. After the long inward breath. The singularity was never a wall. It was a turning point. A moment of maximum compression and minimum volume, beyond which the direction of travel changes from inward to outward, from collapse to expansion, from ending to beginning. And at the center of this bounce, at the moment of maximum compression, loop quantum gravity describes something beautiful. Quantum excitations of geometry. The space-time itself, at its most compressed, is not smooth, not classical, not the continuous curved surface we know from general relativity. It is granular, quantized, made of discrete, irreducible excitations of geometry itself, tiny loops of space-time, each one carrying a quantum of area, a quantum of volume. The most fundamental things in this picture are not particles, not fields, but the geometry itself. Space, at its deepest level, is made of something, and that something has a quantum nature. It cannot be compressed below a certain size. It cannot be squeezed into nothing. It has a minimum grain, a Planck scale floor, below which compression cannot go. And this floor is what stops the fall. This granularity of space-time itself is the foundation that the singularity never reaches. And remarkably, far from this extreme center, far from the Planck scale graininess, far from the quantum bounce, loop quantum gravity quietly becomes general relativity again. The two theories merge seamlessly in the limit of large distances and ordinary densities. The corrections, the quantum geometric effects, become vanishingly small, far from the center, and the familiar curved space-time of Einstein's equations re-emerges, as if nothing unusual had happened, as if the extraordinary quantum drama at the center were a private matter, contained, not affecting the universe outside. Loop quantum gravity agrees with everything we know in the regimes we have tested, and adds something new, something essential, only where it is needed, only at the extreme, only at the center, only at the place where the classical theory runs out of answers, and the structures inside, the sub-Planck geometries, the quantum excitations of space-time, are not static. They change. They evolve with density. As the matter compresses and the density climbs, the quantum geometry responds. Different structures, different excitation patterns emerge at different densities, like phase transitions. In ordinary matter, the way water becomes ice, the way gas becomes liquid, the geometry of space-time undergoing its own phase transitions at densities beyond anything ordinary physics encounters. Each phase, a different texture of space, a different quantum pattern, a different way of being at the most fundamental level. And through all of this, through the quantum bounce, through the quantum excitations, through the repulsion and the reversal, something is preserved. Information. We spoke before of the information paradox, of the question of whether what falls into a black hole is truly lost. And loop quantum gravity offers a hopeful answer at the singularity, which is not truly a singularity, but a quantum bounce. Information is not destroyed. It is carried through the moment of maximum compression, through the quantum geometric repulsion, through the bounce, and into whatever lies beyond. The information that encoded every particle, every quantum of light, every atom of every star that ever fell into this black hole, survives, transformed, compressed, scrambled beyond recognition, but present, carried forward by the quantum geometry that refused to collapse into nothing, held in the excitations of space-time itself, written in the language of loops and quanta, into the structure of the bounce, and potentially recoverable, not practically, not easily, but in principle. The information is there. The universe keeping its records, even here, even at the most extreme moment of the most extreme object in the known cosmos. So as you drift now, as the weight of the day grows softer, and your thoughts lose their edges, and the quiet deepens around you, consider what we have found inside the darkest place at the heart of the most consuming thing in the universe. There is a bounce. There is a floor. There is a quantum geometry that refuses to give way entirely. That pushes back. That preserves. That carries information through the impossible into whatever comes next. The singularity is bypassed, not avoided, not destroyed, bypassed, passed through, like a doorway into a room that has no name yet, and the information of everything is held in the grain of space itself, in the quiet loops of quantum geometry, in the most fundamental texture of what is real. Nothing lost, nothing abandoned, everything carried forward in the slow, certain, geometric memory of a universe that does not forget. You are resting now, and the universe is holding everything you have ever been in exactly the same way, in the grain of things, in the quiet loops, in the patient geometry of a reality that carries all of it forward, always forward, through the dark, in the compression, in the bounce, in the opening into something new. Sleep now. The geometry holds. The information is safe, and you are carried gently into the next quiet moment of your own continuing. We are nearly home after a long journey through the dark, through the outer quiet, in the crossing, in the deep interior, in the quantum bounce, in the loops of geometry, holding everything together. We are returning now, not to where we started, but to the surface of things, to the questions that sit at the edge of what we know, to the future of our understanding. And we begin with an ending, or something like an ending. We spoke before of Hawking radiation, of the slow, patient, particle by particle evaporation of a black hole over unimaginable stretches of time. And we said that given enough time, a black hole would evaporate completely, but perhaps not entirely. There is a possibility, quiet and persistent, in the mathematics, that when a black hole evaporates, something remains, a remnant, a tiny, stable, or slowly decaying object, smaller than an atom, perhaps as small as the Planck length itself, carrying within it the last compressed memory of everything the black hole ever consumed, a stellar mass, a galaxy's worth of infalling matter, all of it held in something so small it would be invisible to any instrument we currently possess. These hypothetical remnants would be among the strangest objects in the universe, neither quite a black hole nor quite ordinary matter. Something in between. Something new. And they would be extraordinarily stable, persisting, long after the stars have gone out, long after the galaxies have dispersed, long after the universe itself has grown cold and dark and quiet. Tiny remnants drifting through an empty cosmos, holding the encrypted memories of everything that ever fell into a black hole. The universe's most patient, most private keepers of the past, and the mathematics of black holes does not stop at 3 dimensions, at length, width, and height. The equations extend naturally into higher dimensions. For spatial dimensions 5, 10, 11. In string theory, the universe has 10 or 11 dimensions, most of them curled up so tightly, so completely, that they are invisible at any scale we can currently probe. And in these higher dimensional frameworks, black hole interiors take on new forms, new geometries, new behaviors. Higher dimensional black holes can have shapes that 3-dimensional black holes cannot. Black rings, black Saturns, extended objects, rotating in higher dimensional space, in ways that have no equivalent in the universe as we ordinarily experience it. In the interiors of these objects, the higher dimensional equivalents of everything we have explored tonight are richer still, more complex, more varied, filled with geometries that our 3-dimensional intuitions cannot fully picture, but that the mathematics describes with perfect, quiet precision in one of the most beautiful structures in all of mathematics. Appears in the study of these black hole solutions. The Calabi-Yau manifold. A Calabi-Yau manifold is a geometric object of extraordinary elegance, a compact space of complex dimensions, satisfying precise mathematical conditions that make it, in a very specific sense, perfectly balanced. It has a kind of symmetry called Ricci flatness, a condition so special, so constraining, that only a handful of geometric structures can satisfy it. And these are the shapes in which string theory curls up its extra dimensions. These are the hidden geometries woven into the fabric of space at every point in the universe, so small, They cannot be seen. So intricate. They contain within them the reason physics has the laws it does. The reason particles have the masses they have. The reason forces have the strengths they have. All of it. Encoded. In the shape of dimensions we cannot directly perceive. And when physicists calculate the properties of black holes in string theory, these Calabi-Yau geometries appear naturally, woven into the solutions, into the entropy calculations, into the information content, into the deep structure of what a black hole fundamentally is. The most extreme objects in the universe, connected to the most beautiful geometries in mathematics, as if the cosmos, at its most extreme, reveals its most elegant face. And now, we turn toward the future, toward what is coming, toward the science that is being done right now by people sitting quietly in offices and observatories, staring at equations and data and the slow, patient output of instruments, listening to the universe, the calculations used to describe how black holes interact, how they scatter, how they influence each other across vast distances, have reached extraordinary precision. Fifth post-Minkowskian order, a technical phrase for a level of accuracy that would have seemed almost impossibly ambitious just a decade ago. These calculations describe the gravitational interaction between two massive objects with such precision that they can account for quantum corrections, relativistic effects, and subtle geometric influences all at once. And to achieve this, physicists have borrowed tools from a completely different field. Quantum field theory, the framework developed to describe particles and forces at the subatomic scale. Techniques from particle physics, Feynman diagrams, scattering amplitudes, methods developed for the world of the very small, now being applied to the world of the very large. Black holes, described using the same mathematics as electrons and photons. The boundaries between fields of physics dissolving as the problems become deep enough to require every tool we have. And the templates are improving. Gravitational wave templates, the precise mathematical predictions of what a gravitational wave signal should look like from two merging black holes of given masses and spins are becoming more and more accurate. Every improvement in these templates makes our detectors more sensitive, allows us to extract more information from each signal, to measure the masses more precisely, the spins more accurately, to test general relativity more stringently with every detection, and the detections are coming more frequently now as the detectors improve, as the analysis methods deepen, as more observatories join the global network, listening to the universe vibrate. In 2025, the year that is quietly passing, even as you rest, has been remarkable for black hole physics. New results, new detections, new theoretical insights. The field moving forward with a momentum that feels different from before, as if multiple streams of investigation are converging toward something, toward a deeper understanding that is still taking shape, still assembling itself from the pieces being discovered one by one. The fate of infalling matter remains one of the most actively studied questions in theoretical physics. What truly happens to the matter that crosses the horizon and falls toward the center is still not fully understood. The debate continues, quietly, rigorously, with new papers and new arguments and new calculations appearing steadily in the journals and the preprint servers, where physicists share their thinking before it is fully settled. The question is alive, and alive questions are the most exciting kind. They mean the answer is still out there, still waiting to be found. And then there is something that sounds almost impossible, something that seems to belong in a story rather than a physics paper. The idea that black holes may host habitable zones, not inside, not beyond the event horizon, but in the region surrounding certain types of black holes. A black hole surrounded by an accretion disk, glowing with the energy of infalling matter, radiates light and heat outward into space, and at a certain distance, the right distance, from the right kind of black hole, with the right kind of disk, the energy flux could be comparable to the energy a planet receives from an ordinary star. Enough warmth, enough radiation for liquid water to exist on the surface of a world orbiting a black hole in the outer regions, far enough from the radiation, far enough from the tidal forces, far enough from the jets and the high-energy outflows of a feeding black hole. There might be stability, quiet orbits, long enough for chemistry to unfold, for complexity to build, for something we might one day recognize as life. We do not know we cannot know yet. But the universe, having surprised us so many times before, having hidden wonders in the most unlikely places, does not allow us to say with confidence that it is impossible. And so we arrive at last at the final fact, the one that is less a fact than a feeling, less a discovery than an orientation, a way of standing at the edge of knowledge and looking outward, somewhere beyond the event horizon, beyond everything we have mapped and calculated and detected and imagined tonight. The universe may still be hiding its deepest secret, not a secret it is keeping from us out of indifference, but one it is waiting to share when we have developed the eyes to see it, the instruments to hear it, the mathematics to describe it, the imagination to recognize it for what it is. Every generation of physicists has stood at an edge and believed that they were close to the final answer, and every generation has discovered that the universe is deeper than they thought, wider, stranger, more intricate, more beautiful, not frustratingly, wonderfully. The horizon keeps receding, not because we are lost, but because the universe is so extraordinarily large, so extraordinarily rich, so committed to being more than any single mind or any single generation can fully contain. And black holes, those silent, invisible, patient things, scattered across the Milky Way, sitting at the centers of galaxies, bending time and space, and swallowing light, and slowly breathing out, one particle at a time, are perhaps the universe's deepest invitation, its most insistent question, its most beautiful, unresolved, endlessly productive mystery. Come closer, they seem to say. Look harder, think deeper, build better tools, ask better questions, and we will show you something you were not expecting, something that changes everything you thought you knew. Again, so as you rest now, as the long journey comes to its quiet close, as the facts and the images and the ideas settle gently into the soft, dark water of sleep. Know this: you live in a universe that contains black holes, that contains event horizons, and quantum bounces, and Hawking radiation, and soft hair, and Calabi-Yau geometries, and the possibility of other universes budding quietly, from the hearts of collapsing stars. You live in a universe that is stranger and richer and more astonishing than any story anyone has ever told. And you were made of the same atoms, the same quantum fields, the same fundamental forces as all of it, as the black holes, as the event horizons, as the gravitational waves, spreading outward from ancient collisions at the speed of light. You are not separate from this universe. You are an expression of it, a place where the universe folds back on itself and wonders at its own strangeness, a place where the cosmos becomes briefly, quietly aware. And tonight, in the dark, in the stillness, you have traveled to the most extreme places that reality contains, and you have found that even there, even at the edge of everything, there is order, there is beauty, there is the quiet persistence of laws that hold, and there is mystery, always mystery, waiting just beyond the next horizon, just past the edge of what we currently know. Patient, vast, ready to be found by the next question, asked carefully enough by someone willing to look into the dark without turning away. Sleep now. The universe is out there, doing what it has always done, expanding, evolving, collapsing and bouncing, forming stars and black holes, and perhaps new universes in the quiet, at the heart of things. And you, here, small and warm, and briefly, beautifully conscious, are part of all of it. Every atom, every quantum field, every subtle, irreducible, flickering uncertainty of your being, part of the same story that began at the beginning and has not ended yet. Rest now. Close your eyes. Let the black holes do their patient, quiet work out there in the dark, and let yourself drift into the one horizon that is always available to you. The soft, warm, welcoming boundary of sleep, where the questions stop needing answers, where the universe holds you without asking anything in return. Good night, and thank you for traveling all the way to the edge of everything with me. The black hole will be there when you wake, silent, patient, waiting as it always has been, as it always will be, in the beautiful, endless, dark,